And I speak of Vaibhav will be speaking about what I said, eating Python. Eating a better Python. It's kind of all right, cool. So anyway, personally, next week's together, Vaibhav. Thank you guys for carrying the dangerous bridge and making it all the way over up to the website. And I had to still listed and all that, so hopefully it wasn't too much for most of you all. The thing I want to talk about today is really just an interesting thing that we've been working on for a bit. I really want people, I'd love to hear people's thoughts on, in general, what they think. But before we get started, how many of you think that software is the same as it was a year ago? A direct answer. It's really not. It's really fundamentally different. And in so many ways than I ever had. And when I first started this, I mostly grew up writing C++ code and assembly code. And I was like, I love C++, best language ever. And 3 years ago, I discovered Rust, and I was like, what the fuck was I doing with my life? There's just a class of mistakes that are never possible in Rust, which makes it possible to not just like build software that's good, but to build a team that can reliably build software that's good. And I think that is the more important part than just writing good software. And yet, to my dismay, every other engineer out there has decided for application code, we will use TypeScript or Python. And what I hate about that is both those languages are basically lies. Like you write it, the type system lies to you all the time, the runtime lies to you, everything is basically made up, and you do whatever you want. There's a great talk called WAT. If you haven't seen it, go watch it. It's freaking hilarious. So one of the missions that we started on was, what if you made a language that doesn't have any of the invariants of Python and TypeScript, but also doesn't feel like Rust, but yet has all the invariants that Rust might have? And it starts with the goal of what happens if AI is going to be the primary author of reading and writing code, but humans' main job is to understand code. And what does that really mean? I'll show you a really simple thing. You'll probably see code. If you can't see in the back, sorry, come closer to me, I don't like it. But as you go through this, here's simple code. It probably looks like TypeScript. That is the goal from a looking perspective. But what we're able to do is every single piece of code can automatically become this a quick little diagram. Every single bit of code automatically becomes a quick little diagram that is able to be referred to without ever having to change the code. And there's semantic code. The diagram isn't just a one-way thing. It's actually like a quick little thing that takes you to the exact line of code that's modifying it. What's really interesting is if you actually run the code, I'll talk about how a group of people writing Rust. What's really interesting is the runtime can actually embed into that as well. Just give you all the information you might want to have as you're understanding code. So now, without actually reading a single line of code, you can start to understand this. But you can go a little bit further and start asking really interesting questions. So when I think about what code does, what does code really try to do? Well, oftentimes models are just trying to understand your code. That's it. So let's just ask it to describe a function called greet. And just gives you the information right away without having to ever do grep. Because grep is effectively useless in many ways. Because what does grep do? Grep searches for the string. Well, what does describe do? Describe uses the AST to give you exactly the right information with the dependency that you're looking for. If you describe the refine image function, and remember, models are the ones writing code. What it will actually do is actually start skipping the context out and only give you semantically useful parts and start dropping parts of the system away, but gives you all the information you need to start grabbing the whole information from underneath that. Now, as you go through this, the other thing that you really need to do to start actually understanding the code is, what do? Well, you read the code, well, you look at the diagram and understand it, model it. You search the code, which describes what you're going to do. You search the standard library, which you can just give it virtually keep searching all the way down really fast. And instead of having descriptions of the code living in like the web or any other place, the code becomes a single source of truth at all times, and everything is self-describing. So if you're curious how to do something like, what is a function, you just ask it, and it just tells you. If you're curious how async works, well, jokes on us, we don't have async because async is the same. we have something like go routines because I think that's a much better model. And it tells you that. It tells you to use spawn and then shows you that and go look it up. So anything that you're ever trying to do becomes really quickly evident with the semantics behind it. But the next level of starting to understand code is actually like the execution model. What you really want to do is you want to run code. And what I want to do when I run code is just call 1 + 2. And I just want to quickly run it for me and start executing it on the fly like a REPL. And I mean, this is some of the places where a lot of systems languages kind of miss out. And even TypeScript has missed out, which is, I've noticed it's in model usage a lot. They offer in Python -C almost all the time. So quickly just run a script to do stuff. Python -C is great, but like, if you guys remember, I have a Greek function. Why can't I just call the Greek function and run the C? But not a Greek function. You don't think that's good picked up. That demo didn't work. Let's try something else. Why can't I just like run the Greek function really fast and just like have it dump out what I want without having to go through it? Every function effectively quickly becomes CLI because the Greek function help command tells me that it takes in name parameter. That's the strat I give. If I ask it a name parameter, it's got a name. I don't have a name. What is it? And you don't have a name? Well, Paul. It was like running really quickly. So everything suddenly becomes a quick standalone system that you can just go through. Now, last thing you probably want to see is pack. And pack, what a lot of people do, it actually takes any single function that you want, quickly makes it into a standalone binary that makes it quickly self-sufficient on any environment that you want. And this is kind of where I think like having the thing that's actually backed by actually like Rust, which does run anywhere, maybe different to run the closet, it runs in any architecture choice. You want target like any of these architectures, you just compile it and make it run for any architecture anywhere else. And like I think I'm part of it, it's super helpful to make this kind of stuff happen. But when I think about really having code that is super, super useful to make happen, what I think about is how does code run anywhere in a way that's easily describable to both humans and models? And I take that a step further. So I'll show you some of the stuff that we really love about Rust that really inspired this. I'm going to do like the result type. Why? It's simple. Better than exceptions. Exceptions fucking suck. But what do you hate about the result type? Nothing. It's okay. I'm trying to rock it. But what I hate about exceptions is about result types is that they're incredibly viral. If you accidentally forgot to make something a result type, well then, how many lines of changes do you have to make underneath upstream to make that one? We thought about this problem really, really hard. And we came up with a slightly different answer to that. That was basically like Rust exceptions, but with slightly nicer syntax. I'll Rust result types, not exceptions. If exceptions are not exceptions, they're control flow. And anyone that's otherwise, it's fine. So this function, foo. Foo is a function that throws a string and returns a name. Well, the compiler and the type signature tells you that right away. Retry is a function that takes an lambda, calls that lambda, returns a t-type based on that lambda. It doesn't actually retry yet. I'll show you how to fix that. So in this case, the demo function, what should the demo function do? It should throw a string. And I've written this out in my contract in the function well, which is explicitly required, which is explicitly requiring user string. I'm going to change this to temp 5. Now all of a sudden, you get a compiler error where you broke this contract. You're seeing that this is actually also going to throw in. So what you get really quickly is result types without result types, where the error value becomes a thing that the compiler automatically infers from every single place in the code base without having to go through it. So if you want to go catch errors, let's say you want to catch all int errors, boom, I'll break down this. Now this error goes away because this function throws an int. I'm catching errors. Take time at the int. I'm going to run this log, turn a null. Boy, it's already. I'm going to turn a null and then go do something with it. All other errors get caught. If I change this back to a string, what do you think happens? Well, that becomes unreachable really fast because the compiler knows all the exception types. And what's nice about this is, unlike Rust error types, which are purely mandated everywhere throughout the code base, which is what makes it viral, kind of like Java's raises clause, that Rust is much better implementation of that. The difference here is this becomes gradually optimizable. So if you're using AI to write a lot of code, what ends up happening is AI can choose what you're doing. You can write prototype code and then quickly harden it to reliable production code as you want. Your API surface, great. Explicitly write throw statement to make sure that doesn't break. Everywhere internally, just use synchronous to make that kind of do what you want it to do. I'll pause for a question. Can you say your name before you ask? Do I have to? No, I guess anonymous. Go ahead. Okay. What is the retry functions type? The retry function type has a secret thing, which is actually inject the generic parameter. See throws callback. That's how we actually do that. Yeah. Yeah. So what my comment was, if you want to have exceptions being done this way, there's the type 6 system technique that allows you to avoid the throws under every function. That would call like modal effects. Have you heard that? No. What does it do? So modal effects basically allow you to it's similar. Maybe pick me after. Yeah. Okay. But yeah, the idea. Question. Yeah, I have your name. I'm Ben. Okay.
Why doesn't you say it throws straight?
Why doesn't? Wait, say that again.
So previously demo wouldn't compile unless you had throws string next to it. But why doesn't Foo say throws string?
The way that you can think about throws in a type signature is if you choose to write throws, you're basically writing an invariant that says this must not throw anything but a string. So if the compiler infers it to throw an int, sorry, chat. I'm used to my. Now this becomes the compiler error. So you can use this as kind of like a guard, like a type checker.
I see.
So it's actually
If the throws at the end is optional, right?
Exactly. Throws is optional. By default, the compiler will infer it. And you can do a better, it's like for API context. You want to ship an API, write your throw signature. If you want to prevent it from breaking, be stably done.
But do a certain competitor throw.
That's easy. Throws. Never. The never type.
And you can use term more than one type.
Yeah, we have much of that again. Love Rust AP types. I also love union types. And that should just work. And it tells you that we're not throwing them in, because obviously if I check it, I'll tell you this. Thank Jack.
Don't worry, Chelsea, stop asking questions about the feature visiting. And maybe you already asked to retry that. What happens when you have a function that take like a function pointer's argument or a TR function where it's like unclear what it had?
Yeah, like this one.
Yeah, what happens?
Yeah, so what we actually do is we actually look at the compiler and we say all callback parameters get automatic. Technically, this is compiled down to this without you having to write that code. And it basically becomes an automatic generic that this kind of works. And we do that with like arrays and everything. You make your types do the magic it needs to. And when you get this, now the inference does the work. This function throws E. So obviously the caller can also throw E now, because you're not catching E. That's like the hack that we have around this. Obviously, if you have containers with lambdas, and we have to do something else, we can't automatically make container generic. That changes variants and arrays and stuff. But we do throws never by default in all data types. So you have to do anything. So if you want explicit throws, you have to make it generic explicitly, and for function parameters, we do the same thing. Name, gigas. How do these exception signatures interact with back? With what? Back? Oh, but like the binary thingy? Mm-hmm. Well, it's error service values. They just happen to have a call pattern. So there's nothing special in pack. Like if you raise an exception at the end of your call stack, we sort of non-zero. So if you were to chain act functions together undefined, I don't know that. If you were to pick the result of Bruno's function back into a function, like if you were to pipe binaries together, yeah, It'd be the same as having a status code non-zero in most Unix files. So like whatever like the Unix command does when the prompt, they're sort of like build the package. But yeah. Okay. Sorry, I like to ask people's names so it makes it a slightly familiar thing. And I like to dog people's name. And maybe I'll remember follow. What's this? You get scared with him, writing review, option right? And when you they're like this. So this will not work because this opens up the type, but it's at feet. It kind of just works like it does the TypeScript, except it's not made up on a line. Real. The runtime actually models the types, and we have like reflections, so you can actually get all the type information about time as well. The only reason, as much as I love having tag unions, I also really love tag unions. So the ESP effect really hard to Now, I'm going to show one last thing. There's a few more things I can show, but I'll show one last thing. Now, this shit is kind of weird. I acknowledge that. It's very, very weird. And obviously, no one's going to write the whole code down. It'd be dumb to say it. I'd use a different word, but it's very dumb. So we went a little bit further and we said, what if you could just call BAML from any language of your choice and just make it interoperable? You write the code here and just becomes embedded. Not only does it work as a standalone language, it also works as an embedded language. I think I have some code I can show for this, so I'll just show like the Python side. It also works in Node now, and it soon will work in I think Go and a couple other languages. So we have namespaces. Everything gets code gen into a thing called BAML SDK. This is a Python function. We have the demo namespace. You saw that over here. You have classes like where you go? There we go. In this class called greeting over here, you can create a greeting class in Python that does this. It's bound to the underlying BAML object, basically like F5 on steroids, but it's type safe. So shout obviously will return a string because shout yeah. Repeated will also return a greeting object because greeting object over here. So now imagine you can write the same code once, but apply it everywhere. I think it's a promise of awesome, but like usable in many different environments with the same exact runtime, same exact purpose, stacking others in the bit. You remember that retry function that we had? This function is a Python function. You can actually set Python function across the wire and have the BAML function run it, and it will guarantee it. If it returns an exception that doesn't match, you'll actually get the Python exception back through the wire. But you'll also get the right YAML exception underneath the hood. So the idea is, yeah, shit should just work. And we try really hard to make things just work. But shouldn't it work the other way? So if I have a BAML program, can I have it call my REST rates? So we would barely ergonomic by fashion. So in theory, yes. In practice right now, no, not with Rust. And the reason for that is we don't yet have a tie on our team somewhere yet. We don't yet have a concept of like make code, like frankly, as much as I love Mute and like most things like honest, most people in the world don't. And we have to acknowledge that. But BAML is like really immutable everywhere else. So in order to actually make a binding with Rust, we have to first add the read-only declarative. In BAML, once we have read-only, we can then introduce F5 to Rust. Once we do that, we should be able to do that. However, if you're part of the compiler team, you can do interesting things. And for that, we actually have a whole bunch of stuff that we do. That's like I got something there. Like we have a special thing, BAML slide. Yeah, those are kind of library stuff. We have special things in the BAML code, and you can do things that are like Rust functions in our compiler. And then the compiler will bind them to like actual Rust functions that we maintain and bridge. And we have a whole bunch, around it. We do want to make this like eventually like first class thing. So again, BAML compiles using the Rust compiler everywhere. So like technically, if we make it nice, we should be able to make bridges and packages of BAML that you can write that are like the NumPy equivalent, where you can implement something purely in Rust if you want, but bridge it across the wire and do all the hard work you can really allocate it. just not the top priority right now. We just want to make the rest of the language work. But that is the goal. We want to basically, C Python was amazing, but it's horrible to work with and have to write against. So we kind of want to get it off of it. Yeah. I mean, even not to this speak. Well, we have a collector that basically runs C# garbage collector. Like we have like we copied a bit of Go at C# garbage collector, and it's like, I don't know, write a lot of good code like that. Like you just test it and you find leaks, and when there are problems, you fix them. But there's not really good, bad way. So again, I love traits. Traits are awesome in Rust. But say the word trait to someone else that doesn't write Rust, and so much. People like the word interface, so we have interfaces in BAML. And the interface will allow you to go, let me see, I might have we have iterators, so iterators allow you to go through things, associated types, and a few other things, get generics. Again, sadly, my background mostly in writing systems code. I don't want to. There you go. That's all right. Eyes here. There you go. That's the right answer. Yeah. So we have an interface syntax that we think is much more appealing than I think the trait syntax. It makes it easier to maintain, but also I think issue very similar guarantees.
Still bad. It sounds like you guys don't have a borrow checker or WLC. So what happens when I do something nasty with unions, readops, and violate the type systems?
You can't. You can't. They're waiting. I thought what they have. So I'll tell you one of the ways that you could break it. It boils down to threading. Multi-threading it usually break the type system. It's not. I don't think it should be possible to break the type system in any other way. And if they're single-threaded program or multi-threading, like that. Multi-threaded where that happens. I'll show you how we deal with this. So in multi-threaded systems, that example somewhere in here. I have a Claude code quote somewhere here, but okay. The way that we do threading is we use spawn. You write spawn, everything in this code block now executes under the thread. They just automatically happen. Eventually, you're going to wait for features. We don't do .await because again, that's the ability that normal does, Python TypeScript. But we have to use await space. But this does everything you want. But technically, once you're spawning things, you might have a variable that points to a union that is captured, and a different function changes that variable. We have one variable union, you did a match on, and you kind of got in the wrong arm. You did that. How do we get around this? We just refuse to type now on some situations. So you might do a match. You might say that something is some value. I'll just show you what this. But we'll see if this works live, but we'll find out. What's a function that lives on ints? Yeah. Max value. There you go. Zeros. Leading ones. Oh. Right. Okay. Oh, well, there's a bug. Okay. If this becomes a capture value that goes through a different thing, let's say let equals. Compiler bug. What this should do is this should actually refuse to actually let you bind to X directly. And now if you have this, then this will actually complain, not let you rebind. I'll bind to actually say as X every single time. The way you get around this, if you say let Y, and now you can do something with this. because now it's factor. So this is how you have to do reflagging. This is the one trade-off where it's suddenly ergonomic, but threading is very important. I think async is horrible because I don't want to have two code bases, async and non-async, same things I want to go through. When we solve that problem in Slate. I think we're out of time. Cool. Thank you guys for listening. Hopefully this thing comes out if it is.